Hello, now we're going to talk about straight lines in 3 dimensions. So everything turns out pretty much the same. If we have some r, and we'll call that r is x, y, z, and we have some position vector a, right? Then that's going to be x1, y1, z1, and then some vector in 3-dimensional space that is parallel to the line, to some line in space. So we have some line in space, right? And we're trying to come up with a vector equation in 3 dimensions. I guess I should draw a 3-dimensional graph right here the best I can. Let's say it looks like this. This is x, y, and z. And then you have some line going through space. Same exact thing happens in our previous video. Then we're going to have coming from the origin, that would be a, and then this would be r. That's our vector a, and this is our vector r. And then some parallel vector. We have some u vector in space, right? Same thing happens, right? Where u is use of 1, use of 2, use of 3, the same concept happens. We can write our vector equation in 3 dimensions, where it's going to be vector a plus some scalar lambda times u, times the vector u. And then we can write this as x, y, z is equal to, if this is our position vector, that's going to be x1, y1, z1, plus some lambda, and then our vector u, use of 1, use 2, use 3. Good. And this is our vector equation in 3D. So this is the vector equation in 3 dimensions, right? And then we can write our parametric equations the same way, right? But this time it's going to be x is equal to x1 plus lambda use of 1. Then our y is equal to y1 plus lambda use of 2. And then z is equal to z1 plus lambda use of 3, right? So this would be our parametric equation of a line. And if we wanted to find our Cartesian equation, we can eliminate the parameter, right? And if I eliminate the parameter by solving for lambda in each situation, I'd have lambda, and I'd have x minus x1 over use of 1. Solve for lambda over here, and it would be y minus y1 over use of 2. And then finally solving for z minus z of 1 over use of 3. This actually turns out to be my Cartesian equation. And it turns out in 3 dimensions, this is the only way we can write our Cartesian equation. I think in my last video I said 2D when we eliminated a parameter, and I called it another form of the parametric equation. That's incorrect. This is the Cartesian equation. We just don't usually use this form in 2 dimensions when we had just like these two. We use, our slope-intercept form and a point slope. But in Cartesian equations, there's no way other than to write a line in Cartesian equation this way. And there you go. So we're going to use all 3 of these to solve a few problems. So let's go ahead and look at the first one. Example 26. It says given a is equal to 1, 3, negative 1, b is equal to 2, 5, 0. Represent line AB by a vector equation, a parametric equation, and a Cartesian equation. So first thing I'm going to do is figure out what my vector is from A to B. So it's 2 minus 1 is 1. 5 minus 3 is 2. And 0 minus a negative 1 is plus 1. So that's the vector and the line, and then I can write my vector equation. I can use any one of these points, but I'm going to use the first one, so that would be 1, 3, negative 1, plus some lambda, and then 1, 2, 1. So this would be this is my vector equation. For B, my parametric equation, taking this vector equation up here, I could say x is equal to 1 plus a lambda. My y is equal to 3 plus 2 lambda. 3 plus 2 lambda. And then my z is equal to negative 1 plus lambda. And those are my parametric equations. And then finally, C, my Cartesian equation, would be by eliminating the parameter, and I can write it as x minus 1 over 1. I can write it as y minus 3 over 2. And my z is going to be, I'll add 1 this way, so it would be plus 1 over 1. And this is my parametric equation. I could write it just like this, x minus 1, y minus 3 over 2, and then z plus 1 over 1. I guess I can divide it by 1, so I'll just write it like this. You can write either form you can use. Sound good? All right, next question we're going to look at is example 26. It says a line L has a Cartesian equation as such. Find the coordinates of one of the points on the line L and a vector parallel to L. So let's see. So first thing, it's not quite in the form that I want. I can see what's going on over here. I'm just going to reform this so you can see where I can find a point, and then I can find the vector that's parallel to L. Well, I can write that as x minus a negative 2 over 3. I need this to be in the proper form, right? Y needs to come first. So I can call this y minus 1, but I'm going to make this a negative 2 on the bottom. See, y minus 1, if you could see, it's the same as that. Now, here, I don't want a coefficient in front of this z, and I can say z minus a half over a half. Another way you can see what I did is this is over 1. I multiplied by a half to both sides, keeping everything the same, and it goes right here. Now, once it's in this form, then I can go ahead and find a point that's on this graph, and it's going to be negative 2, 1 and a half. Now, that's the exact point that's on there, right? And then I can find the line that's parallel to it, because under here gives me my u vector, gives me the components of my u vector. This is my u sub 1 component. This is my negative 2 and my half. And it just needs to be going in that direction. It doesn't need to be those exact ones. Sometimes I can write another vector. Let's just say it's v, because it's different from u. And if I multiply by 2, I can get a better vector. I'm going to have 6, negative 4, and 1 is another vector I can use. Maybe I want to write that in linear combination form. So 6i minus 4j and plus k is another way that I can write that parallel vector. Sound good, guys? Thanks.